Did you solve it yet? Did you get it? Did you get an answer? 360? We should. But we'll solve it together. All right, bullet has angular momentum. Even though it's moving in a straight line, it is not moving in our reference plane. So we have to factor that in when we're doing conservation of momentum. So what is our reference plane? Well, the center of mass of the stick is our reference plane, like we said before. Because that's the point of rotation. That's what we're going to reference everything to. Okay, now we're going to do some conservation of momentum. Initially, the only thing that's moving is the bullet. But that's the only object that has angular momentum. Okay, thinking about what equation you're going to plug in, well, you're given mass and velocity. So you're probably going to use an equation with mass and velocity. So we're going to use our MVR. So that's going to be the mass of the bullet times its initial velocity times the radius, which we said that's the distance of closest approach. We'll plug that in. That's all we have for initial angular momentum. In our final picture, okay, bullet is still moving, so it still has angular momentum. So this is going to be its final velocity times r. But the stick is also rotating. It is also going. So we need to include the stick too. So since that is rotating with some angular speed and it has a moment of inertia, we're going to use I omega. And really it's essentially plug and chug from here. So I'll plug in a little bit more. So MVI, the radius of our bullet, well, that's going to be the distance closest approach, which is this d over 4. And remember, it doesn't matter where that bullet is. The radius is always that distance of closest approach, whether it's there, or all the way over here. So the radius is the same for both parts. And then we're going to sub in 1/12 mass of the stick. And then the length of the stick is just d times its final rotational speed. Okay, so this is the equation that we basically need to make pretty and then solve. So let's see. So I put all my bullet info on one side. D. So I'm gonna do that equals 1/12 mv squared omega f. And I'm gonna make this prettier and solve for our final angular speed. So I can cancel out 1d on both sides. And then I'm just going to get our final omega by itself. So that gives me, okay, that's what I did. So I factored out an m. So this is essentially m over 4 times vi minus vf. So I'm going to multiply by 12, divide by big M. So that gives me 12 times little m over 4 big M. And I got to get that distance over there. Okay, so if you plugged in numbers already, that's fine. But it is important to know how to solve these with just variables, even though it is not real. When I do plug numbers in, if I did it right, I get a final angular speed of 360 radians per second. So that's how you set up conservation of angular momentum when you have some linear terms and some rotational terms. Just plug in whatever you know, and they'll come into numbers. They'll stay as variables. One last example, we're going to do a merry-go-round. Now, this bullet hitting stick, this is a really common type of problem I see for AP problems, and so is this type of merry-go-round problem. So you need to know how to do these. So the scenario for the merry-go-round, we have, now, I'm going to use this exact problem, but we have this merry-go-round. This is kind of an aerial view of it. You know, so you got all the bars, all the kids stand and barf. So the child is running. He's like, hey, merry-go-round. So this is the kid. He runs and he jumps on it. He runs and jumps on this merry-go-round is at rest. Stationary merry-go-round. So I want to know, after he jumps on, what is the angular speed of that merry-go-round? Now, some info you need. So our initial angular speed of the merry-go-round is obviously 0. The I of the merry-go-round, I'm just going to give you, that's 500 kilogram meter squared. Radius of that merry-go-round is 2 meters. And our kiddo over here. So this is a kiddo with a mass of 25 kilograms. I don't know if that's a big kid or not. But he's running at 25 meters per second. I'm pretty sure it's like exceedingly fast. Maybe I meant 2.5. I did. That seems really fast. Yeah, let's make that 2.5. 2.5 meters per second. 25 kilograms. All right, that's all the info. That's what you get. Now you need to set up conservation of momentum. Start with, it's always safe to start with this equation. A lot of times that might even give you a point. Who knows? Now sub in the equations you're going to do to find angular momentum. For the initial scenario, only the kiddo is moving. And you're like, hey, but he's moving in a straight line. But he has angular momentum because this is our reference. Okay, this point of rotation of the merry-go-round, that's our reference. He's moving in a straight line outside of that reference plane. So our initial angular momentum is going to be the mass of the kiddo times the initial velocity of the kiddo times the radius, which will be the radius of that merry-go-round, because that's the distance of closest approach. And then in our final scenario, when he jumps on, hey, they're stuck together. So we have a perfectly inelastic scenario. So in that case, we add the I of the child plus the I of the merry-go-round. You're like, what? Moment of inertia of a kid? That's weird. Just treat him as a blob, okay? mr squared. And we'll plug in. So just treat him, just plug in mr squared for the moment of inertia of the child, and you know the moment of inertia of the merry-go-round. And we're going to multiply those by their equal final angular velocity. Plug and chug from there. Pause it, see if you can solve it if you haven't already. Okay, mass of the kid, 25 kilograms times his initial velocity of 2.5, and that radius is going to be 2 meters. That's that distance to closest approach. All right, moment of inertia of the kid, which is just going to be mr squared, so that's 2.5 times r, again, still at 2 meters, plus I of the merry-go-round, which you just plug in as 500, and then you get a final angular velocity of 0.21 rads per second. All right, so those are some examples of angular momentum. There are more problems in the book for you to do, and I'll try and have some more for you to do as a review. Enjoy!